09. Yes, great. Okay, so you see my screen. So last week we spoke about the Bosnian condensation, and I basically hinted at the fact that you can use light in order to trap these atoms, and then what we wanted to have are basically two condensates, so that there are two traps. But what I didn't discuss is actually how that works. So how can you trap atoms using light? And this is the first topic that I would like to discuss today. The model that I'm using to use is really a minimal model. So of course, if you don't write it at home, I mean, it's much more complicated, but I think the main physics is captured by the model that I'm going to present. So what I would like to present is basically a minimal model for optical traps. So what is the model? The model is actually a model that we have already seen. So it's just some cavity. So let's say omega 0 A dagger A. Plus some plus a spin, so let's say omega z sigma z, plus some interaction. And let's take the simplest case of interaction, which I would like to be A sigma plus A dagger sigma minus. So this is this James Cummings type of interaction. And this is, okay, a single spin. So this spin is actually the two-level system is basically the atom. Okay, so this is the atom that we are speaking about, and the cavity is going to be a laser field that we actually should shine on the spin. So let me assume that this perturbation is small, and we will discuss what we mean by small. So we discussed it as some perturbation, and then what we do, actually, you don't really need to do that, but it simplifies your life. So let's assume that the cavity is highly occupied. We are in a laser, such that we can do a mean field approximation and assume that just the cavity field is just some classical field. So A e to the minus I omega ct. So we assume that the laser field. So and this A bar is just some number. Okay, that's the idea. So this is basically describing a laser, as we have discussed extensively in the first lectures. Okay, so what we end up is basically sort of a time-dependent Hamiltonian. So HT is going to be some omega z sigma z. I don't need to care about the cavity anymore. The cavity is already solved. And plus G, we're going to have some A e to the minus omega ct sigma plus A dagger sigma minus. Sorry. Okay, let's call it plus emission conjugate. Okay, good. Okay, so now the question is, how do you deal with such a time-dependent Hamiltonian? And essentially, what we would like to do is to consider some sort of average Hamiltonian that comes out of this rotating field. So the simplest thing that you can do is basically just take the time average. Okay, so what I would like to perform is something that is known as the Magnus Expansion. The idea of the Magnus Expansion, it's essentially the same as time-dependent perturbation theory. It's exactly the same idea, perturbation theory, with the difference that now what we are usually in time-dependent perturbation theory, you work on the wave functions. There is a wave function, and you try to correct it according to some perturbation. Here, what we are the Magnus expansion is a way by which you can modify the whole Hamiltonian. So you think of the Hamiltonian itself, and you say, well, the unperturbed Hamiltonian, so this h of t should be some h0. Okay, in this case, h0 is just this omega z sigma z. So this is the unperturbed Hamiltonian plus a number of terms. Actually, the goal is to transform this Hamiltonian in time-independent Hamiltonian, which we can call it as H effective. And the way that we derive H effective is in perturbation, as a perturbative expansion of H of t. So in other words, what we are trying to do is to write, instead of having, say, the time evolution, as you all know, is the time ordering e to the minus H of t dt. And this is sort of a complicated thing to do because you need to, this is U of t. So this is the time evolution for some generic time-dependent Hamiltonian. It is very complicated because it is because of the time dependence, and so the Hamiltonian at different times do not commute, and hence this is not e to the e to the minus I. Okay, let me tell you what it is. So what it is, according to the Magnus expansion, it is approximately given by some. Actually, it is exactly given by e to the minus I h effective t. So we are trying to transform this time-dependent Hamiltonian into a time-independent one. And then what we do, we expand h effective in orders of the perturbation. Okay, so this is the idea, to have an effective Hamiltonian, which is time-independent and takes into account the time-dependent terms. And it is analogous, it is very similar to time-dependent perturbation theory. And what it does for you, so if this perturbation, so this is now our perturbation, so this is now our V of t, this is our perturbation. So what you need to have, the first term is something simple, it's just the time average of the perturbation itself. Okay, so you just say dt prime. You just, you consider the time average of the perturbation. This is the simplest approximation you can do. Forget about the time dependence, just take the average. Now, if the Hamiltonian is commuted, this would be exact. I mean, if we didn't have this time ordering, meaning the time ordering means that the Hamiltonian different times do not commute, then what you would have is just, well, no problem, perform the integral, and that's it. That's what would be for a time non-commuting classical Hamiltonian. But in the case of quantum mechanics, things become more complicated because the Hamiltonian that you apply at some time t does not commute with the Hamiltonian applied at time t prime. So you cannot just really write it as an exponent of some integral. What you really need to do is to evolve each time separately. Okay, that's the difference. This is where quantum mechanics come in. And so what you can do is to do a perturbation theory. And the perturbation theory will tell you that the first term is just the time average, and the second term has this form. So it is 1 over t integral 0 of t dt prime v of t commutator v of t prime prime integral dt prime prime from 0 to t prime. Okay, so you have a commutation relation. Again, this comes because if the perturbation different times does not commute, then that's what you need to take into account. Where note that okay, yes, that's what you need to do. Okay, this is basically this time-dependent perturbation theory, which we will discuss in a moment. Okay, questions? No. Okay, good. So the first term vanishes. The first term vanishes because, yes?
So this is exact? This is not an approximation?
No, this is approximation in the sense that there are then other terms. There are many terms, and they all look the same. Every time you have one more commutator, I mean, it has the same shape. You add one more commutator, one more integral, one more commutator, one more integral. So it's actually quite simple to write it down. Usually, so if you could resum the entire series, it would be fine, but here we can't do it. So we're going to take only the second term. Okay, now the first term vanishes because you have this e to the I omega t, so e to I omega t, if you take long times, it vanishes. This is like a cosine potential in function of time, so it averages to 0. So that goes away. And the term that we are interested in is this second order perturbation. So let's focus on the second order perturbation. So let me call it, say, H effective 2, which is, well, okay, we can even write it. As a effective is going to be H0 plus, we have this integral. So we have 1 over t dt prime 0t 0t prime dt prime prime. So this is prime and prime. Okay. So now what is the v of t? So we can take out g square, and we can even take this a bar square. Okay. Remember that this was a bar, this average. We have assumed that in a mean field approximation, we have assumed that it's just time, it's just a constant. And then what we have is e to the minus I omega c, basically t prime minus t prime prime. Actually, let me do it. So let me do it a little bit better. So, okay. So e to the minus omega c t prime, sigma plus of T prime plus emission conjugate. Commutator with e to the minus I omega c T prime prime sigma plus T prime prime plus emission conjugate. Let me explain you one important thing, which is that what do I mean by sigma plus T prime? Why did I say sigma plus T prime? The reason is that we are performing here perturbation theory over some bare Hamiltonian. As a consequence, what we do is we introduce the time dynamics of the bare Hamiltonian to sigma plus T prime. So sigma plus T prime is going to be sigma plus, which is evolved according to the Heisenberg equation of the free Hamiltonian. So it's basically sigma plus e to the minus I omega z omega zt. Okay, so this is important. So every time that you do a perturbation theory, you work essentially in the interaction picture. So you put you already take into account the bare Hamiltonian in the evolution of the operators. Otherwise, it wouldn't be a perturbation theory. Okay, so this is what I mean here. So we can rewrite this expression as omega z plus g squared a bar squared over t dt prime prime. And here what we have is essentially e to the minus I. So maybe I think this should be a plus here. So e to the I omega c minus omega z t sigma plus emission conjugate. This is one, and the other term is e to the minus I omega c minus omega z t sigma plus emission conjugate. Okay, good. And then there is a commutator. So what this tells us is that essentially the effect of the cavity on the spin depends on the frequency difference between the cavity and the spin. I think even if I didn't derive it from first principles, I think this is something quite obvious. That what really matters is the frequency difference, or as is known as the detuning. So we define delta, the detuning is going to be omega c minus omega z. Okay, and we use the usual notation by saying that if omega c, so if delta is positive, means that the frequency is larger than the spin frequency. So this is what is known as a blue detuned. And if delta is smaller than 0, it means that the frequency of the cavity is smaller than omega z, then we call it the red tube. Okay, this is the usual notation from just the spectrum of light. Okay, cool. So now let's look into this commutation relation. And in the commutation relation, it basically, so what you have is sigma plus. So sigma plus commute. So that drops out. And what you have is basically the non-trivial part is the commutator between sigma plus and sigma minus. Okay, so there is a commutator between sigma plus and sigma minus. And what this does for you is going to give you basically h0 plus g squared a bar squared over t integral dt prime prime times sigma plus commutator sigma minus, which is
2 times sigma z.
Sigma z, yes. So factors of 2. We all agree that by the way, even in the Magnus expansion is a factor of 2 here, but we don't care about factors of 2 in this course. So there is a factor of 2 maybe, but the important thing is that there is a sigma z. This is the key point. So there is a sigma z here, and okay, good. Times what? Times e to the minus I delta t, e to the minus I the plus I delta t. So this is prime, this is t prime prime. Okay, so the one contribution comes from this. So sorry, this is one contribution. Okay, this is t prime, and this is t prime prime. So the first contribution gives you e to the minus I delta t prime, and the second contribution comes from the initial conjugate, so it gives you e to the plus I delta t prime prime. Okay, so to summarize, what we have is g squared a bar squared t integral dt from 0 to dt prime from 0 to t dt prime prime from 0 to t prime sigma z e to the minus I delta t minus t prime minus t prime prime. Okay, plus, so g squared a squared t, integral from 0 to t dt prime. So the integral dt prime prime is going to give us essentially, so we have e to the minus I delta t prime. That's something, okay, this step was pretty stupid. Okay, so I take out e to the minus I delta t prime prime, and they have this integral over the over t prime prime, which gives me 1 over I delta e to the minus I delta t prime prime from 0 to t prime, from 0 to t prime. Okay? Yes, you agree? Maybe there is a minus here.
And sigma z somewhere also.
And there is also sigma z, yes. Okay, so what you get here, you see where we are going. So essentially, and here there should be a plus. So this term will give us two terms. They give us 1 plus e to the I delta t prime prime. Now, when I perform the integral over t prime, this one will fall off because of this rotating term. So we are left only with the term. No, this is e to the I t prime. Okay, so there is a term that exactly cancel out. You know, this e to the delta t prime exactly cancels the e to the minus the delta t prime, and what you're left is equals to g squared a bar squared over t times the integral from 0 to t dt prime of 1. Okay, so this one comes because of the cancellation between these two oscillating factors. This one term falls off because of this rotating term. We are assuming that the times are long, so you know you can average them. Okay, and so what this gives us for this, and there is also time divided by delta. So what we obtain essentially minus I. So what we obtain is essentially I g squared a bar squared divided by delta. Okay, so this is the Hamiltonian. Actually, to be precise, there is an I factor that we need to take into account. You know, when you look into the Magnus expansion in Wikipedia, you need to be careful because the Magnus expansion in Wikipedia is for linear equation of the type something like, you know, d psi over dt equals to a psi. Right? This is the way that you will see in Wikipedia. But in Schrödinger equation, there is an additional I to it. So essentially, you would need to multiply. This is I H effective. I here. There is an I everywhere. Okay. This I essentially, yeah, right. So there are I's everywhere. There is an I here, I there. You know, there are many I's. No, here there is no I. And so what you end up is that, so to summarize, in taking into account the I's, we have the IH effective equals to IH0 minus I g squared a bar squared over delta sigma z, or in other words, what we get is that the H effective is what? Is basically omega z sigma z times 1 plus 1 minus g squared a bar squared over delta. Okay, so this is the key. The key result is the fact that the energy of this two-level system depends on the strength of the laser. Okay, this is also known, it has different names. It is also known as the AC Stark shift, or as the dispersive shift. By the way, this is also the way. This is also what is used in order to say measure spins, right? So this shift is actually, there is also, if this is now, if you go focus on the spin, you think of the cavity. Also, the cavity is shifted. So these shifts can be used actually to measure the spin. But here in this case, what we have is that the energy of the two-level system depends on what? On g squared over delta, which is some effective coupling, times a bar squared. And a bar squared is the intensity of the laser. So what it means, but notice this minus sign. The minus sign is very important. So now it depends on the sign of delta. So if delta is positive, as we said, this is blue shift, then what it means is that minus g squared a bar squared over delta is going to be negative. In other words, it means that the energy of the two-level system goes down. Okay, again, here it now depends also on the spin, but let's assume that the spin is the ground state. And actually, there is no, because we are shining the spin out of resonance, there is no reason to believe that the spin should go up. So of course, if you prepare the spin in the excited state, fine. But usually, if you wait some time, the atoms will go to the ground state. And as a consequence, sigma z is going to be, oh, well, this would be negative. So well, we would have, you know, this. Let's put it yes. Let's put it this way. So let's put a plus here. Let's put the plus here. So essentially, it means that, you know, let's assume that sigma z is negative, and so when the detuning is positive, then this factor is positive, meaning that the energy of the spin goes down. Okay, and the other way if delta is negative. So now let's think of an atom inside the laser field. So the atom inside the laser field experiences a shift in its energy. And the more the laser is strong, the more the shift will be stronger. And what does that mean is that the atoms will be essentially essentially trapped in regions where the laser light is strong. Again, depending whether you are blue shift or red shift. But if you are blue shift, then unless I have made some errors in the sign, for one of the two possibilities, the laser light will trap the atoms in regions of large intensities. Now, usually a laser, so if you look at the profile of a laser, so this is now X, and this is the intensity of the laser, what happens is that there is some Gaussian. So in the middle, the laser has stronger intensity, and in the sides, it will have weaker intensities. And so in this case, this can be used to create, again, depending on whether you use positive or negative detunings, to create a trap for the atoms. So whether either a trap or something that repels atoms. And this is usually used to trap atoms. Okay, so this is the basic physics of laser, of optical dipole traps, where the key idea is that really the energy of the spin is proportional to intensity of the laser. And that's what you need to what you need to learn for the practical purposes that we are interested in. Okay, good. Okay, so how can we use it to make things interesting? And this is related to experiments that I'm going to show you later. Situations in which the intensity of the laser changes over space. And one way to do it is to use, so what I would like to discuss now, which is the main topic of this lecture, is what happens if you have, how can you simulate a disordered potential? Disordered potential. And the idea is to use basically a disordered intensity field. So use a laser in which the intensity field, instead of being just a boring Gaussian, which is a trap, it's interesting to trap atoms, but it is constant. The idea here is to use instead some laser field whose intensity changes over space. And we are going to discuss how this is done. Okay, basically these are sort of, let me just tell you in one word the way you do it. You just take your normal laser. Okay, so this is your laser. And then you put a small piece of glass. It's called a spacle. Okay, so just a disordered medium which diffracts the light in all directions. Okay, and so by diffracting light in all directions, you obtain a laser field, a laser field whose intensity varies over space. And this is equivalent to having a trapping potential that changes over space. Okay, I'm going to show you a bit more the details about the experiment in the second part of the lecture. So how can we model it? Okay, the way we model it is basically by thinking of these atoms that are trapped. What we have is basically some free electrons, sorry, not electrons, atoms. So we are going to have, the Hamiltonian is going to be two parts. The first part is basically just the kinetic energy of the atoms. Okay, this is each kinetic, plus some potential. Okay, and the potential is basically going to be some integral over space, Vx. So Vx is going to be the potential at position x, which, as we discussed, is proportional to I laser. Okay, so if you want this Vx could be something like g squared over delta times the intensity of the laser, the function of x, something like this, times the number of particles, of atoms in this position. Okay, so we can write this in a more compact way by recalling that what is the kinetic energy. So the kinetic energy is basically sum over k squared over 2m psi k dagger psi k. Right? If you have a particle, this is just the number of particles with a given momentum, and the energy per momentum is k squared over 2m. Okay, so this is just usual second quantization of free particles, and you can also rewrite it as integral over x. You just perform a Fourier transform, and then what you get is 1 over 2m integral dx psi dagger of x dx squared psi of x. Okay, so this is with the minus. So we can rewrite the whole Hamiltonian in a very compact form, by writing some dx psi dagger of x times minus 1 over 2m. Okay, so here in this step, I just noticed that the k squared is the Fourier, is in Fourier space. If the Fourier transform of k is the derivative, so k squared will give you minus the derivative. So what you get is minus 1 over 2m psi dx squared plus some d of x psi of x. Okay, so this is the Hamiltonian of free particles. Notice that this is the standard form of second quantization. So what you have here essentially, this is essentially the Hamiltonian in the first quantization, right? This is just the Hamiltonian as you learned it in undergraduate first quantization. And in general, to go from first quantization to second quantization, you just sandwich this Hamiltonian of the first quantization with psi dagger on the left and psi on the right. And the idea of the second quantization, the difference between first quantization and second quantization is that first quantization is good if you have one particle, second quantization is good if you have many particles. Now, the truth is that as long as you are dealing with non-interacting particles, then there isn't much difference. So you actually, this whole formalism second quantization is really not much useful. I mean, you really don't need it. I mean, if you have non-interacting particles, you can really think of each particle as just an Hamiltonian with some disordered potential. But then this second quantization allows you also to introduce interactions. So in addition to that, you may have also some H interaction, which describes the interaction of the atoms among themselves. Okay. So let's first discuss the simplest case, so without interactions, and then we will discuss the case of interaction. This is also the way that this was studied experimentally. So the first experiments referred to a state without interactions, and then they took into account also theoretically. So let's first start to discuss the case of with no interactions. So what we have is just, so in case, as I said, without interactions, you can really work in first quantization. You can say that H first quantization is just minus 1 over 2m, the second derivative plus d of x. So this is just the first quantization. And you can ask yourself, what happens of particles in a disordered potential? So if v of x is just a Gaussian, then you know, it's just a parabola, you know how to solve it. Okay, this is undergraduate. The question is, what if v of x is a disordered potential? And this type of question was first discussed by Anderson and led to the idea of Anderson localization. So what I'm going to do now is, first of all, so how many of you are familiar with, have learned Anderson localization before? Okay, not many, a little bit more, okay. Okay, So let me review. So what is the basic phenomenon of Anderson localization? So in Anderson localization, you have this potential, and it's going to be some random potential, and you are trying to find the eigenstate of that potential. Or alternatively, and this is actually the same. So you could ask yourself, let's assume that I am initially, so I prepare my Hamiltonian in some, so I prepare my particle in some wave function. So this is a psi 0 of x, this is my initial wave function. And I ask myself, how does this wave function propagate in space? So you all know that if there was no potential, then this would propagate ballistically, right? So if it was a Gaussian, it would expand. You can just analytically solve it. It's very simple, and you see that it expands over time in a linear. So the width grows linearly with time, and it is called the ballistic expansion. The question is now what happens with disorder. So clearly it will be slower. So the wave function will grow slower. But the question is actually, does it really grow or not? And what Anderson found is that if you wait long enough, the wave function will be trapped. So at initially it will start to grow, but then at some point it will stop. Okay, so this is a psi of x of t going to infinity. So even if you wait infinitely long time, still the wave function is going to be confined in some space, and this is what is known as localization. What is the basic idea of this phenomenon? So the idea of the phenomenon is that you may ask yourself, say, what is the probability of reaching some point? So what is the probability of finding psi of x for large time? And this is just going to be proportional to psi of x t goes to infinity squared. Okay, so let's say I sit here. I know that at the beginning, the particle was finding this wave function, and I want to know what is the probability of finding it in this wave function after long times. So the way you need to do it semi-classically is to say, well, what you need to do is to basically take, because this is a wave, you really need to take like many particles that are located in each of these different positions, and then let them evolve in time. Okay, and when they evolve in time, they can sort of go to the right and go to the left, and eventually they will get to the point that they're interested in. But because the potential is, but what happens is that while moving with this potential, they acquire a phase. Okay, so this is the time evolution means to acquire a phase, and the phase that you acquire as a function of time is proportional to the energy. So depending on where the particle is, it will acquire a different phase. As a consequence, when you go from the initial position to the final position, you actually need to sum over all possible paths that go from the initial position to the final position. And each path will acquire a different phase. So at the beginning, I assume that they are all a Gaussian. So basically, I put them all in the same phase. That this is what gives me say, let's assume for simplicity, initially this was a Gaussian, so they all were real. Okay, so all the points had the same phase. When the particle expands over time, the different paths acquire a different phase. And eventually, what I need to do in order to compute the probability of finding myself in the end point is not to sum the probabilities, but to sum the wave function. And because all the waves acquire different phase, they destructively interfere. And eventually, if I go far enough, then I need to sum so many paths that it sums up to 0. Okay, so this is the phenomenon of Anderson localization can be sort of summarized, sort of explained or understood by saying that this is a destructive interference. Destructive interference between the different paths. And again, this requires a disordered potential. Why? Because if you just have a normal potential, then all the paths, when you move to the right and move to the left, you acquire exactly the same phase. So all the paths arrive exactly with the same phase. And in contrast, when you have this disordered potential, then you acquire different phases depending on how much you went to the right and how much you went to the left. So this disordered potential is what gives us these random phases that eventually lead to the localization. Of course, the more disorder there is, the faster the more the wave function is localized, because the faster it is to dephase, right? So if the potential is almost constant, then these phases sum up to roughly speaking the same value. But in contrast, if you have large fluctuations of the disorder, the wave function will be more localized. Okay, so there is a relation between the intensity of the potential, this V of x, okay, this typical V of x of the disorder, and the localization length. Okay, okay, this is generally speaking the idea. But then the question, so this approach was formalized by a very famous work, which is known as the Gang of Four. It's called the Gang of Four, with some literature reference. And these are four physicists, which is Abrams, Anderson, Licciardelli, and Ramakrishnan, who in 1979 wrote a very influential paper, which is called The Scaling Theory of Localization. Okay, quantum diffusion in 2 dimensions. Okay, scaling theory of localization. So what they did, they tried to study this localization effect using a scaling argument. And the scaling argument is actually relatively simple. I think I'm going to give. Originally, I plan to teach it in the lecture, but I think it is going to be much more useful for you if you solve it as a homework. So I will give you references and also some guidelines. It is really not too complicated. But let me just highlight what are the key aspects of this argument. So the key aspects of the argument is to consider some piece of material, let's say a block of material of size L. Okay, so this is L. So, okay, this is in case of 3-dimensional. And what you want to compute is the conductivity of this material. The conductance of this material. Okay, so the conductance is like the conductivity, which is like the resistivity. So this is the conductivity per unit dimension, per unit. Okay, so this is G. It's a G. Okay, so you remember the difference between conductance and conductivity. Conductance is resistance and resistivity. So resistance is R, and resistivity is the resistance per unit. So it is basically R divided by the volume times it's R divided by the size. So clearly, if you take a piece of material and make it longer, the resistance will grow linearly with the system size. And in contrast, if you if you make the resistor larger, so if you take a wire that is wider, that has a wider cut, it will lead to a larger resistance. So the resistivity is sort of, it's like per unit volume. So what you do, you divide by the length of the material. Okay, so this is in the case where you have a system of size. There is a cut the cut has width A, the area A, and D is the okay. So this is G. So so R is called the resistance, and rho is called the resistivity. Okay. In the same way, you have G, large G, and small g. So large G is sort of the total conductance, which is like sort of the total, if you want. And there is G, small g, which is the conductivity, which is sort of the per unit. Okay, good. So then the question is, if I have a material and I make it larger and larger, how does the conductivity change per unit? So in the case of the metal, the theory is given here. Okay, so this this is basically telling you how the resistivity and hence the conductivity. Okay, the conductivity G, small g is 1 over rho, and large G is 1 over r. Okay, so here I have already told you for a metal, how does the conductivity change when you increase the size of the system? And the question, in contrast, this is for a metal. Okay, so this would be the case of a metal. In contrast, for a, yes?
Excuse me, yeah. So just something which is not very intuitive. When you increase the cross section A,
yes,
the resistivity should be lower, like the resistance, right?
Yes, I think you are perfectly right. So, so you are saying I should do the opposite, should do R divided by A times D. Right? So you are saying, so the resistance is, no, because there is, no, the resistance becomes larger. No, yes, when I make it, no, what I said before was correct. So when you increase, say, the, right, exactly, right. So you're right, you're saying the cross section, when I increase this cross section, the resistance goes down. Hence, in order to have something that does not depend on the cross section, I need to multiply by A. Okay, so this is sort of the intrinsic property of the material is rho. That's the property that doesn't change with the system, with the size. That's why I multiply by A, because I know that in principle the resistance should go down, at least for a metal.
Yeah, I missed the multiplication with R. Yeah.
Yes. Okay. Excellent.
Thanks.
Yes. Yes. Very good. So this is for a metal. What happens in the opposite case? So the opposite case would be an Anderson insulator. Okay. So the opposite case is the Anderson insulator. So in the Anderson insulator, what we have is that the wave function decreases exponentially, and hence it is natural to assume that also the conductivity decreases exponentially, right? Because what is the conductivity? The conductivity. The conductivity is essentially the probability of having an electron that processes from one side to the other. So the bigger the material here is, the less probability you have that such an event will occur. And so the assumption of the Gregor-4, based on the idea of Anderson localization, was to assume that there are materials, which they call Anderson insulator, in which the conductivity will go like e to the minus L over xi. Okay, the bigger the material is, the less conductivity you have, but in an exponential way. Okay. And what they did basically was to write a theory, a scaling theory that connects these two limits. Okay, and the assumption was that the conductivity depends only on the size of the system. And so they sort of wrote a theory, and again, I'll give it as a homework, in which that connects between these two limits. And what they found was that depending on the dimensionality, there can be either sort of a smooth crossover from one limit to the other, or a steep or a phase transition. So what they found was that for V that is larger than 2, if the dimension is larger than 2, that there is really a transition between these two limits, meaning that the more I increase more and more the system. And so depending on some critical value, if I start from, say, G that is smaller than G critical, then I will eventually become an Anderson insulator. While if G is larger than G critical, then it will become a metal. So there is really a critical point, a critical transition between the two. In contrast, when the dimension is smaller than 2, then there is no transition. There's no transition. And what will happen is that the only way to connect between two limits is to assume that when you increase the function more and more, when you increase the system size more and more, you always end up in an insulator. Irrespective of, and the case D equals to actually, I would say, the smaller than 2. So the critical dimension is 2. Also, even in 2 dimensions, eventually it will take very, very long time. So initially, so what happens is that for a small piece of material, it looks like a metal. Then why? Because the wave function is very broad. Actually, in 2 dimensions, what will happen is that the wave functions are like power law. But okay, so let's take the 1-dimensional case. In 1 dimension, it means that all the wave functions are localized. And when you increase your system more and more, the conductance become more and more exponentially suppressed. So at the beginning, think of it this way. Think of a situation in which this is your localized wave function. So when the system size is small, if you take a small system size, then you say, oh, no, I don't see any localization. So for small chunk of materials, it looks like a metal. Then you increase the system size more and more, and eventually you end up with a huge system like this, and then you say, oops, and you say, oops, there is a problem. Now I don't, so that's this. What is this flow telling us, right? It tells us that when you increase the system size more and more, you start feeling the exponential suppression, and eventually you always end up in another solution. Okay, so this is what I wanted to tell you. And again, the exact derivation, I think it is much more useful if you do it on your own. Then you will see how the mathematics. I can show. I remember when I first learned it, I was in class. Of course, the teacher taught me. He said, "Oh, it's very, very nice." Then I forgot it right away. And it was not until I had to teach it, I said, "Okay, wait, I need to, I need to do the derivation on my own." So I basically help you, and instead of postponing your learning time to when you will be professors, I help you and make you learn right now. Okay, good. So let me just one last comment, and before we take a short break, is another type of potential, which is called an optical lattice. Optical lattice. So beforehand, we had an optical trap, and now we have an optical lattice. The idea of the optical lattice is to have just 2 counter-propagating lasers. What do you obtain when you have 2 counter-propagating lasers? With the same wave.
Interference?
Yes, which type of interference? How is it called?
Standing wave.
It's a standing wave, exactly. So when you take 2 counter-propagating waves, you obtain a standing wave, which means that the intensity of the laser varies in space. So there are positions, say, where the field always vanishes. These are the nodes. And so at the nodes, there is the intensity in 0. So the input okay, this is some time, and another time what we will find is something. So what I'm drawing is the electromagnetic field as a function of time. So as a function of space for different times. So there are places that are known as antinodes, where the intensity changes a lot, antinodes. And there are other places known as nodes, where the intensity is always 0. So at the antinode, so eventually, by using this second-order perturbation theory, what you see that what matters is not the field itself, it's the field square, right? It was proportional to field square. So at the antinodes, you have a lot of intensity, and so the atoms will be attracted. And at the antinodes, and then the nodes, the intensity is 0, and so the particles are less attracted. So what will happen in this situation is that the particles will be attracted to the antinodes. And again, it depends on which detuning you're using. So either to the antinodes or to the nodes, depending of which of whether you are blue detuned or red detuned. But the important part is that there is periodicity. Okay, and so this is the way that you can generate a periodic potential for the atoms. And it is very useful when you try to mimic condensed matter systems, because like in condensed matter systems where there are the atoms that are fixed and the electrons that hop around, here you have a laser that creates a periodic potential and the atoms that hop in analogy to the electrons. Okay, so this is a system that will be analogous to a system of, instead of having electrons that hop on a lattice, you have atoms that hop on an optical lattice. Okay, this is a well-known, I'm pretty sure you've all heard about this. Okay, good. So let's take a 10 minutes break. We will start again at 11:05, and I will show you some slides, about these experiments. I will show you the speckle experiment, some one in optical lattice. These are beautiful experiments. We really, all these drawings that I'm showing you, we will see that in an experiment. So it's not just a theoretical dream, but something that you can really visualize. And I think this is really nice. And there is also, if time is allowed, we will also see what happens with interactions. So in the case of atoms, you can also study the interaction. We'll first see experiments without interactions, and then we see what happens with interaction, which is also very, very interesting. Okay, so stay tuned, and we will.
Emmanuel, can I ask a question?
Yes, please, Jonathan.
About the transition between Anderson localization and meta. So this G that this condition about G being smaller or larger than G critical, if G depends on the length at any time, what does this G mean?
So, okay, very good, excellent. So this is G, you're very right. So this is G0, okay? So there is always, the scaling limit always breaks down at some point, like any scaling limit. So eventually when we reach a situation, we have, say, the atomic size, okay? And so this gives this, so the assumption here is that G depends on L, and there is, it follows these two either, sort of an Anderson insulator or a metallic behavior only for large system sizes. So there is an initial sort of a small chunk of material that you start from, and then you increase more and more. So depending whether you increase, you started from a G that is smaller or larger than the critical, this will either go up or down. Okay. So eventually, as any scaling argument, eventually the scaling argument have what is known as an ultraviolet cutoff. I mean, at short distance means that at high frequency, short distances, it will break down. And this is where you start your analysis. And then, you increase more and more, and you see in which direction you go.
I see. So either way, it will start, the conductivity starts to decrease as Anderson localization.
Right. So let me just add one more comment, which is that as you will see in the homework, the whole idea is to look at the derivative of G as a function of L. Okay, this is, and so if it is positive, then G increases. If G is negative, it decreases. Okay, and you can, well, I don't want to spoil the homework, but that's the idea. So the transition is really this. You look at these sort of these derivatives as a function of L, and you see that in one case you cross 0, and in the other case it's always negative. So in low dimensions it's always negative. So when you increase G, when you increase L, G goes down. Okay.
Thanks.
Okay, thanks. Okay, then see you. Okay, welcome back to the lecture. You're welcome to turn on your camera if you want, so they can. Okay, welcome back. So first of all, I have breaking news for you, which is that we are going to move to a hybrid format starting from next week. So for those of you who wish, there will be the possibility to meet in person. And so still the course will be taught also on Zoom. So you can use, it's hybrid, you can use both options, the one you prefer. But instead of sitting in your own home, if you want, you can basically have a sort of a more lively experience by coming to the to Bar-Ilan, and I'll send you the details of it's a room 303 in physics theory. I'll send you the details by email. Okay, great. So okay, you can see my presentation, and I have a pointer. I know how to advance. Okay, good. So let me discuss a beautiful experiments about this Anderson localization. And what you see here is the type.
We see the tablet.
Oh, you see that tablet. Okay, thanks. Okay, great, great. Now you see the presentation? No?
Not yet.
You should. How about now?
No.
No?
Maybe stop
Oh,
sharing.
wait. Resume share. Okay.
Yeah.
How about
No.
now? Okay, good. Okay. So a measurement with mobility edge for 3D Anderson localization. So as we mentioned, in 3 dimension, there is a transition between localized and delocalized. You can either think of it as a function of different materials. So think of changing the properties of the materials, this G0 that we were talking about. Or another possibility is to think of eigenstates at different energies. So it turns out that in general, there is going to be a threshold between, say, low energy states that are localized and high energy states that are delocalized. In general, the more, the lower you are in energy, the more you're localized, the more you feel these high potentials that sort of try to prevent you from propagating. So in general, even classically, the lower the energy is, the less mobility there is. And quantum mechanically, this means that the localization length in general is smaller for lower energies, lower energy eigenstate. So the more you increase the energy of the eigenstate, the higher you get. The more the localization length becomes broader. And in 3 dimensions, there is a threshold above which it's completely delocalized. So this chi goes to infinity, and the wave functions are delocalized. So first, how you create these potentials, and this is schematically shown here. So there are 2 laser fields, and the laser fields that they are realized by crossing some basically piece of glass that makes that creates for you this light. And the reason you use 2 spectacles is that you're trying to use the speckle both modifies both the intensity and the phase of the field. But the most important effect is in the phase. So usually the light that comes out from the glass is sort of intensity is almost uniform, but what changes is the phase. So by having the interference between 2 speckles, you're translating the information from the phase to the intensity, right? Because the intensity of the interference depends on the phase difference. And what really the atoms feel, as we mentioned, is a squared. So they are not really affected by the phase of the light, but rather the intensity. And that's why you're looking for an interference. It is analogous to the case of, this laser, these counter-propagating lasers that forms an optical lattice. So in general, in order to create some intensity field, the easiest way is to modify not the intensity of the field, but the phase, and then having an interference between 2 patterns. And here you see two instances of these speckles, depending on the, probably these are two different cuts of the same speckle. We don't have time to dwell into the details of the potential, but what you see, this is potential. You see X and Z, Y and Z, so these are two different cuts. And what is shown here is probably a simulation of the intensity of the light in the different positions. And basically, this is this sort of shallow, this random potential that I was drawing here is shown here. Okay, so the key observation is what is shown here. This is the key result. What they do, they prepare all the atoms in some localized wave function, and then they measure so this is a BEC. The reason they use a BEC is just because then you have more atoms and it's easier to measure. But at this level, this is just non-interacting particles. You could do it just with a single atom at a time. It just will take you forever. So they use a BEC. There are many particles. They're all in the same wave function. Initially, they're trapped in a Gaussian sort of by a parabolic potential, which will give you a Gaussian wave function. And then the Gaussian wave function becomes larger and larger as a function of time. And what you see here are different values of VR. So VR is the intensity of the laser light, which is proportional to the intensity of the potential. So, and what you see here is that by increasing, so if you have no potential, the potential is very weak, and then you see that the Gaussian increases very rapidly. I mean, within just a few milliseconds, it has already expanded by several microns. So it expanded a lot. While when you have this periodic, with this disordered potential, the wave function expands much slower, and and the larger the potential is. So here the potential is given in units of temperature. This is because at the end of the paper they also studied the dependence of on the temperature of the BEC. That's why it is useful to express energies in terms of temperatures. But this, just think of it as the potential. This is just the width of the potential. Okay, say the maximum to minimum width. And so what you see is that the more the potential is, the larger the potential is, the more the wave function is localized. And if you focus on the grid curve, what you observe is that initially there is an expansion. So when the wave function is smaller than the localization length, it expands, and then it starts filling the localization length and stops growing. So there is always an initial increase. Notice, yes, there is an initial increase followed by some threshold, and this is also shown here. So this is D would be the diffusion coefficient. So you can sort of take a linear linear fit to these curves, and this will give you the diffusion coefficient. The diffusion coefficient is nothing but just the ratio between, it's just the slope of these curves. The diffusion coefficient is the width divided by the variance divided by the time. And again, this is the same plot. These are the same points. So these 5 points here are shown here. Maybe there are a few more measurements. And what you see is that, again, as a function of the potential, the intensity of the potential, the diffusion coefficient goes from from small values to some constant. Okay, I think this blue curve is probably related to the initial width of the condensate. Right, there is an initial width of the condensate that, or maybe even an experimental resolution that they cannot go with. So you see that here it seems like in principle this curve should continue going down. The stronger the potential is, the more there is confinement, but there are limitations. Also, there is another important limitation which is related to the speckle. So the speckle, it has like a random potential, but there is a minimal size of the random potential. So it's not a fractal. I mean, if you zoom in on a specific region, it will in the theoretical model, one usually assumes that the potential at each point in space is different, right? You assume V of X, V of Y is a delta function of X minus Y. There's no correlations. But in reality, the speckles has some correlation. And so this correlation sets for you the minimal localization length. I mean, the minimal localization length is set by the width of this speckle. This is like this sort of red dot. You see that there is a typical size that of these speckles, and this is probably these blue lines here. So you cannot localize your wave functions more than the typical length of the speckle, than the correlation length of the speckle. Okay, so this is an experimental limitation. And there is also another plot here. This is as a function of the energy of the if I'm not mistaken, this is, I hope I'm not mistaken, this is done by considering BC at different temperatures. And what you see here is that there is a threshold from diffusive to localized. Okay, by sort of drawing, so this is for a specific temperature. So from here you can see where is the threshold to localization. And yeah, so you need to repeat this experiment for different energies, and what you will see is that there is a transition from localized to diffusive. So this is this G naught that we are speaking about, and again, this is related to the fact that they are in 3 dimensions. If you repeated this experiment in one dimension, for instance, you would have only localization. All the phase diagram would be localized. Okay, so this experiment was actually done in 2015. And there was an earlier experiment, which I'm showing as a second because it's theoretically, experimentally it was easier to realize. Theoretically, there is some caveats. So let me now focus on an earlier experiment, which is Anderson localization of non-interactive Bose-Einstein condensate. And what is the difference? So the difference is that in this case, so what was the challenge? So the challenge here was to obtain a potential that varied a lot. Okay, so you need to work hard on your speckles, so you have a potential that is really varies a lot over small distances. This was the challenge. So in 2008, what they did, they followed a different approach and said, let's use an optical lattice. Okay, so this would be your, so if you had just the first term, it would be just an optical lattice, 2 counterpropagating lasers with 4 counterpropagating lasers. So if you have 4 counterpropagating lasers, what you get is basically a potential that is a sum of 2 cosine terms. Okay, one from one laser, from one pair of lasers, another for another pair of lasers. And what you do here, you assume that the 2 K1 and K2 are incommensurate one from each other. So this function is shown here. So if you had just J, it would be just a cosine. This epsilon term, what it does for you, it adds these sort of like it's a bit like having a wave. It's like having a sort of a small envelope, right? You see there is like an envelope that changes with some periodicity, and this is the periodicity of K2. So K1 is one lattice, and K2 is the other, and which gives you some small envelope. And now, if you look locally, this looks a little bit like a random potential. So what you actually, in order to map it to random potential, what you do, you first of all assume that J is very, very large. Okay, when J is very large, what you obtain, these are like potentials, and each potential well. So let's now focus on one potential well, on one well. So each well, it's like an harmonic confinement. It has some energy levels. And let's assume that the energy levels are relatively large. So this is to say one energy level, this is another energy level, another energy level. So what you can do, you can assume that for each well, the atoms occupy only one level per well. Okay, so we can assume that the atoms occupy only the lowest level of each well. This is known as the single band approximation. So in the single band approximation, you assume that in each well, there is only one state. This is not true because you have many states. But if the energy is low, so the temperature is small, you can assume that you're occupying only one level per well. Okay? Does this, so now, does this mean that, and this is what is written here. So this Wm, it's the Wannier wave function, so just the wave function of the lowest energy. So M counts the wells, Okay, so this is m equals to 1, m equals to 2, m equals to 3. And this is the wave function of the lowest energy of each well. Okay? Fine? Clear? Good. So what is this term? You tell me, what does the first term do?
Site hopping.
Right. This is taking one particle from m to m plus 1, and you can just think of it as tunneling, right? You're sitting on one well and you want to move to the other well. So this is just tunneling. You can use the WKB approximation, but I mean it has a finite value. There is a finite. Classically, it is impossible, but quantum mechanically, there is a finite probability of moving from one well to the other. So this is a hopping term. And what is the last term? The last term you see it's WM. So this is basically like a projection on the site M. So this is essentially the energy of the site M. Okay, and the energy of the site M is a function. So this is your random potential. Okay, so this is the chemical, if you want, the chemical potential of at a given site. It's not really random. It is. It has a periodicity. The periodicity is 2 pi beta m. Now, if say beta was 1, then actually all the sites would be the same. If beta was say 1/2, then you would have like a sort of a up down situation. But when beta is incommensurate, and beta is really the ratio between K2 and K1. So when beta is incommensurate, then it is almost as a random function. Taking a cosine of some incommensurate number, it's almost as a random function. If I didn't tell you that this was that there was another periodicity, maybe by looking at the picture you would say, oh, this is just a random. You see, it looks like random potential, up down, up down, up down. So okay, so this maps back to sort of a discrete form of Anderson model, of Anderson localization. Okay, these are like non-interacting particles on actually one non-interacting particle. Okay, this is a single particle problem. They call it Bosnian Condensation, but that's this is just single particle physics. So this is single particle hopping on a discrete lattice with some hopping term here, and where the energy of each level is random, actually not random. And this model is known as the Aubry-André model. And the Aubry-André model actually in one dimension, it can be solved, and it was shown that this model has a localization threshold. So if you really have a random potential, then all the wave functions are localized. This is Anderson localization. We discussed it in one dimension. In contrast, for the Aubry-André model, it is a little bit like, it is more similar to what happens in, say, higher dimensions, where there is a threshold. Again, the wave function with low energies are localized, but the wave functions with higher energies are delocalized. So it is essentially a way to realize a random potential, but using something that is non-random. You really shine lasers, with a given k vector. So this is a deterministic way to create something that looks like a random potential. And here you see these pictures, which are these are so the difference. So let's focus on the first row. So in the first row, what you see are many images. Okay, these are distinct images. This is image one. They just put it one next to the other, but you really should think of these each of like one picture. So one picture, two pictures, three. There are many pictures, and each picture is a picture of the condensate. And what you see is that initially the condensate was small. Okay, so it was in a trap, and then as a function of time, it becomes broader and broader, and the ZX, so the vertical axis is the axis of the lattice. So what this BC is doing, so the X direction here is really vertical, in the vertical direction. So the random potential is in the vertical direction. In the horizontal direction, you just have a constant confinement. So no interesting physics occurs in the horizontal direction. All the interesting physics is in the vertical direction. We will see that the condensate expands. And this is in the absence of the other person. So this is with no disorder. Delta is basically this absence. So with no disorder, you see that there is a ballistic expansion. It expands linearly with time, at least theoretically. Well, roughly, you can sort of draw a line. So the width of the BC should grow linearly with time. And when you when you increase the potential, you see that the wave function is localized. So when you put a large confining potential, here delta is even larger than J. So this is actually, this epsilon is not really epsilon, it's really large. Sorry, let me actually correct. What you need to compare is delta with respect to J. So you need to compare this energy scale epsilon with respect to J. And J is small because it's a hopping. It's a tunneling. So J itself is small. So you can use epsilon also can be small and still be significant. And yeah, right. And so this is delocalized and this is localized. Okay, this is what you see. And actually, they can even show this.
Emmanuel?
Yes.
Can you explain again what delta is?
Okay, so delta is epsilon. So delta is in this model here. So this is the model that you're considering. So J is the delta is just the width of the this is delta. Okay, you look in this picture. This is delta. It is the difference between the minimum and maximum of the potential. This is the variation of the energy of each side. So it's the inhomogeneity. It's basically the disorder strength. Okay, this is what delta. I called it here epsilon. I think I think this is sort of proportion. I think this is probably just this. This is.
Thank you.
Okay, good. Okay, good. And what you can do is as a function of disorder. So again, this is small disorder, and this is large disorder. And what you can measure is say the width of your condensate after some time, and then also here you see that. So this is also, so what, again, if this was just a theoretical model, then the spatial widths would go to 0. Here there is a limitation. The limitation is just the initial width of the condensate. So the condensate itself has an initial width. So clearly you cannot grow more than that. And then you can sort of deduce that there is a transition between localization. Well, actually, in this case, it's not clear. I mean, in this case, you could say, well, it is always localized. You cannot really clearly see the localization threshold, right? Because for any value of the disorder, you see that the width is finite. So you would need to perform a more accurate time scaling analysis to see whether it is still growing or maybe it is just reached some constant value. But anyway, the key effect is that you see that the wave functions are more and more localized the stronger the disorder is. And this is the key aspect of Anderson localization. Okay, good. So we have a few more minutes to discuss another experiment. So this experiment is basically based on this 2008 experiment, and they also have the same model. Okay, so this is now in second quantization notation. So you see there is again the hopping term, and there is this Aubry-André potential, right? This is just the energy per state. So this is just the same amount of time as before in second quantization with an additional interaction term. So in this model, they studied also the role of interactions. Specifically, this model was performed for fermions. And so what you see, okay. So the way that they detected whether the system is localized or not was by performing the following experiment. So they put one particle per site. Okay, there is this lattice. They put one particle per site, and then they measure the imbalance between, say, even and odd sites. Okay, so at the beginning the imbalance is say 1 because all the particles are in even sites. Well, actually, this would be odd. Okay, so all the particles are in even sites, and then what you see is that as a function of time, there can be two situations. Either the imbalance goes to 0. Imbalance goes to 0 means that the particles start, running on the entire lattice, and then there is no more meaning of even and odd, and this would be this situation. This is for no disorder. So in the absence of disorder, you see that the imbalance goes to 0. In contrast, for a finite disorder, what happens is that this imbalance goes down but remains finite. And the fact that the imbalance remains finite means that each particle was not able to, each particle, well, it does delocalized a little bit, but it is still sort of localized around the initial state. Okay, so if each particle remains close to the initial state, then there will be always some higher probability of finding a particle in an even than in odd size. Again, the fact that it diffuses means that the imbalance is not zero. Okay, this is what is done here. So let me now guide you through this. So what is the theoretical expectation? So this graph is as a function of U over J. Okay, and this is a function of disorder. So let's start in the case of U over J is the interaction. So it starts on the x-axis, on the y-axis. Here there is no interactions. Okay, so no interactions. That's the AA, an Aubry-André model. Aubry-André model. Okay, AA. And as we discussed, there is a threshold between localized for large disorder and delocalized for small disorder. Okay, so the y-axis was what we have theoretically discussed here, non-interacting particles. Okay, good. Now, what happens with interactions? And this is a whole field of research that have been very active in the last decade. It's called the many-body localization. So it's a question of what happens if you have localization plus interactions. Let me just summarize in one sentence what was the main finding of this research. But of course, there are many details that we don't have time to discuss. But the main point was that interactions, in a sense, make the system more delocalized. And the reason is that this. So what does it mean interactions? Interaction means adding some term to your Hamiltonian. So in general, when you add terms to a non-Hamiltonian, what it does is like think of perturbation theory. Perturbation theory, you couple the eigenstates of the initial Hamiltonian. So let's assume that you have an Hamiltonian that is localized. So all the wave functions or the eigenstates are localized. Now this term does not commute. The interaction term doesn't commute with the kinetic term. So it means that it is like a hopping. It is like a connection between different eigenstates that are localized. As a consequence, the new eigenstates are superposition of the original eigenstates. And in general, they will be more delocalized. Right? If you have, let's say that the initial wave functions are really very tightly confined. The interaction, it will couple wave functions localized in different spaces. So the new wave functions are superposition of the old wave functions, and they will be broken. So in general, when you have weak interactions, and this is shown here, so let's focus here. So when you have weak interactions, you see that the delocalized region becomes larger. Okay, so with increasing U, the curve goes up. The transition point goes up, meaning that it is more delocalized. Okay, so this is a perturbative argument. It was, again, you can read on many-body localization. The interesting point for this model is that actually, so you put more and more interactions, and the wave functions become broader and broader. But then at some point, they come back. And for really very strong interactions, it is still back to zero. But you're back to the original point. And the reason for that is that in one dimension, that's something also very interesting, which we don't have time to discuss. But in one dimension, strongly interacting fermions and bosons actually can be mapped onto each other. So in effect, you start with a theory, say, of non-interacting bosons, and you make them very strongly interacting. But very strongly interacting bosons are behave for some aspects a little bit like non-interacting fermions. You know what is the key feature of fermions is that they cannot. This Pauli principle. So now think of bosons that they are bosons, okay, but they're strongly repelling, and they're so strongly repelling that actually two bosons cannot be on the same side. Okay, so there is, so it looks like a little bit like fermions, and actually one can do that mapping, so Jordan-Wigner transformation. So one can really map, one dimension can really map non-interacting bosons on the left to non-interacting fermions. So this is what happens here, that by having more and more particles, more and more interactions, you actually go back to some. And the same is, this is on both sides. I mean, you can also take interacting fermions and obtain something that looks like a boson. Okay, so this is the last slide I would like to show you today. Okay, so how we read that? So what is shown here in the x-axis, we have the interaction over the kinetic energy. So the x-axis here is the same as here. Okay. Now, what are the colors? The colors is this imbalance. Remember that small imbalance means localized, right? Sorry, small imbalance means delocalized, because small imbalance, if the small imbalance is small, it means that the particles have run away. So blue is delocalized and red is localized, right? Because there is large imbalance. And the way you should read this plot is by take a fixed delta over J and think of running from left to right. So if you run from left to right, you see is that you start from large imbalance, you go to lower imbalance, right? You go from, say, red to yellow, red to yellow. So large imbalance, small imbalance, and then large imbalance again, which means localized, delocalized, and then localized again. This is what you observe, and this is sort of related to what you see here, where you see that you start from, say, you start a finite delta over J, then you are delocalized, increase the interactions, you become localized. Sorry, you're localized, you add interactions, you become delocalized, and then localized again. So this is sort of this shape that you go from delocalized, localized, and delocalized again. Now, the situation is more complex because you see that actually there is sort of it's not just going up and down, there is also this up, and then there is this sort of local minimum in the middle. Actually, sorry.
Manuel?
Yes.
Yeah, so I see here the x-axis, it actually goes from negative to positive.
Thanks, Nicola. Yes, thanks for stating it. Yes, exactly. So to read this plot, what you should do, you should start from the middle and where you are, say, blue, so you are delocalized, localized, and delocalized. So this is this x-axis. But now moving from right to left, so from the middle to the right, or from the middle to the left, is essentially the same. This is also related to the fact that we are dealing with a dynamical problem. So in dynamical problems, you know that take the Hamiltonian or minus the Hamiltonian is the same, right? Because it's like e to the minus I omega t or e to plus I omega t. If you are studying the ground state of Hamiltonian, then okay, of course, it's very different. I mean, the ground state minus the Hamiltonian is not the same, but the dynamics often, if you start from the same state, it's the same. So this is related to why positive and negative U's are similar. So yes, so that's what you have here. So these sort of you know from localized delocalization and then localization again is shown here. Is shown here by this non-monotonic behavior. That's the key aspect. And again, there's no monotonic behavior going to the right or going to the left. And this line here corresponds to this line here. So this is a non-interacting case. I think, yes, okay, that's it. That's what I wanted to tell you today. So we have seen a lot of topics today. We have discussed, first of all, optical traps. We have seen how you can use light to trap atoms. We have discussed the fact that the intensity of the light is proportional to the effective potential that the atoms feel. And hence one can use, by shaping light, it's much simpler to shape light to create an effective potential with interesting properties. We have briefly discussed optical lattices. There is a lot of work on optical lattices. We didn't have time to discuss this. When I give, there is another course that I give focusing on ultra-cold atoms, and then we discuss many more examples of what one can do with optical lattices. One can study, say, phase transitions, in particular from the Mott insulator to the superfluid. So there is a lot of quantum simulations that one can do with these optical lattices. Here we have discussed one specific case, which is the case of a disordered optical lattice that can be either really just a speckle, so some random intensity, or the superposition of two optical lattices, which lead to this Aubray-André AA model. And we have discussed the effects of localization. We briefly mentioned what happens with the interactions, and again, the whole this is an open field of research. But it was beautiful to see that one can see those experiments really, this is also another experiment I haven't shown you, where they really do localization in the simplest way. So you can look it online. Maybe actually this is an idea for your students, for the students, seminar by the students, where they take atoms and then trap them in. So they build the trap and put all the atoms on the left of the trap. Then they they start the dynamics, and you really see how the atoms in one case, in the delocalized case, they start filling the entire trap. In the localized phase, they remain on half of the. So this was done 0, 1, 0, 1. In that case, they just take the whole trap and split it between empty and full. And you see how in the delocalized case, it fills the entire trap. In the localized case, it remains bounded to half of the region. So it's really beautiful visualizations of Anderson in localization with interactions. Just one last word is that Anderson localization have been seen with photons, right? You can take just the photons and put a random potential with photons and see the localization, and the random medium and see localization photons. Then you would ask, why should I see, what is the difference with atoms? Why should I care about atoms? The reason is that atoms are interacting. So you can go in the regime of many body interacting theories where you can study what happens to Anderson localization in the presence of interactions. And that's something you cannot simply do with photons because photons do not interact. Okay, so that's one key advantage of using atoms with respect to photons. Okay, that's it for today. Next week, we are going to meet in person for those of you who wish and who have, of course, a green pass. And we will discuss about some interesting physics of fermions. Questions?
Yes, if I can ask one question. There is, you said there is a critical value of J the relation, the ratio between J and delta. What happens? So I know what happens when it is it is bigger than the critical value, and what happens if it's smaller. But is there any interesting behavior when you stay at the critical value and?
Yes, absolutely. So, in general, when you go from some function that does not decay to a function that decays exponentially, you can also relate this to some order parameter that decays, say, there is long range order in one phase and short range order in the other. It's something very similar. And in general, what you have at the critical point itself is that you will have some interesting power laws. So usually there are some universal power laws that occur at the transition itself. So usually the transition from exponential decay to a constant, in this case, it's the shape of the wave function, will be given by a specific critical exponent. And so yes, one can study what is the critical exponent of the Anderson localization transition. Now, in these experiments, it's hard to see. As you have seen, you can see localization is very robust, but seeing transition itself is not easy. So these experiments were not able to tackle this type of question. You can do it numerically, maybe you can use other type of experiments. In general, these ultra-cold atoms are not very good for studying, the transition point itself, because it's hard to see. You don't really see a sharp transition. It's not like this order parameter that goes to you see. Yes, you see, it's more localized, less localized. I think this was very strong. It's more quantitative, but really having qualitative transition that's very hard to achieve in these experiments.
Manuel, can we go back to the slides where you showed the localization?
Yes.
Without the interaction, I think it was the first.
Yes. So sorry, one. Let me share my screen. Share screen. Okay. Yeah, no, that's good. That's good. Okay. Yes.
This one. Sorry. More. Yes. This. So the blue one. The reason that everything remains localized, is that because they occupy the lower possible energy state in their system? So no. So what Vlada, is this your name? Yes.
Okay, so what Vlada suggests, he says there is a very simple way to have localization, both quantum mechanically and classically. If you have a random potential and you just go to the lowest possible point of the potential, then there is no way to escape, right? In that, that state is certainly localized. And this is true in any dimension. I mean, you can always do that. But here, in this case, the potential is the BC is much larger than the potential. So if you want, the BC is occupying a huge fraction of sites. It's not a single site. It is not a single atom experiment with one atom in one lattice site. These are, thousands of atoms, and they occupy many of these sites. So you are in a superposition of you are in a superposition of all possible, of many states. So it is really due to these interference effects that prevent you from, it's not just an energetic, it's not a simple energetic argument that forbids you from moving, you're trapped in the minimum. It is really, this interference that we discuss in the context of Anderson localization that prevents you from propagating more and more.
Okay, thank you.
But you are right. I mean, there is, if you want, there is no these sort of very simple localization that you described. Being just in the lowest energy and Anderson localization, it's really a crossover. I mean, the more the potential is, the more you're localized. And when you're localized in a single site, then you can think of something analogous to what you said. So there is a limit. I would say there is what you described is sort of the atomic limit of Anderson localization, that you are really trapped in a single site. But in general, this is not the case. You are trapped over more sites, and the fact that the wave function goes down is really due to this destructive interference between the different bumps. Okay, so thank you all, and I'll send you the link that Vlad asked, and also more information about where we meet next week. Bye-bye.
Thank you.
Thank you.